All right, so here we're going to learn how to graph polynomial functions. Okay, so this is a polynomial function, and we'll talk about that in a second. But to become consider a polynomial function, we need to have all the exponents be whole numbers. So that means that we're talking about positive integers and zero. Now, and zero is a thing we need to keep an eye out for. When we take a look at this thing here, if I want to go and find my x-intercepts, I would start by setting f of x, or y in the other cases, equal to 0 and solving. And we can use the zero product property we've seen back with quadratics to do that. So what I'm going to do is I'm going to do a little bit of a shortcut here, and I'm just going to set each of the factors equal to 0, and I'm going to go ahead and solve those. Okay. Now I'm going to do something a little bit different that we don't necessarily have to do, but might help shed a little bit of light on what the idea of multiplicity is. Okay, so I can split x plus 2, that quantity squared, into x plus 2 times x plus 2. And I can further break that down and set those equal to 0 and solve, right? So I end up with x equals negative 2 and x equals negative 2. So it shows up twice as an answer here. And that's an important idea. So here I get x equals 1, and then the same kind of deal happens over here with x times x, or x squared is x times x. So I get x equals 0 and x equals 0. Okay. So I technically have 1, 2, 3, 4, 5 different x-intercepts for this thing. Okay. Now, the idea of multiplicity is how many times something shows up as an answer. And really, the number of times it shows up isn't really as important as if it's an odd number of times or an even number of times. So what we found in class is that if you have an x-intercept that shows up an even number of times, the graph will bounce off the x-axis. Okay? Meaning that the graph will, if it's below, will come up, touch the x-axis, and then go back down to the negatives, or if it's above, we'll do the same thing but continue into the positives. So I'm going to go ahead and write this, that the multiplicity is 2. Because it shows up 2 times, right? The multiplicity of 1 is just going to be 1, right? So it only shows up 1 time, right? And then 0's multiplicity is going to be 2, because it shows up 2 times, right here and right here. Okay? Next, we're going to go ahead and find the y-intercepts. Okay? And for this thing, a nice little shortcut is that if your x-intercept is 0, your y-intercept is going to be 0. But if you don't see that, you can always go back and do the algebra by plugging 0 in for x and solving. Okay, either way you do it, you'll end up with that y-intercept is 0. The degree of this function tells us how the ends of the graph will behave, so the end behavior. So in this case, I have a lot going on up here, but really if I want to take a look at the degree of this thing, the only things that actually affect the degree are the x's. Okay, so the plus 2, the minus 1, that negative 1/2 out front really don't have any effect. But if I rewrite this as x squared, x, and then x squared, right, ignoring all the other stuff, this goes back to our properties of exponents, which is that if the base is the same and we're multiplying, we add our exponents together. So this is x to the 5th. So this has degree 5. Okay? And once I know that I have degree 5, I can see that the leading coefficient is going to help determine our the ends of our graph, or both ends pointing up or down or in the negative direction, whatever happens to be there. So the leading coefficient, really it's not the number that's as important as the sign of it. Okay? So if I take a look at this thing here, the original function, the only thing that's going to affect the leading coefficient here is going to be a little space here, that negative 1/2. I have the x squared, I have the x, and then I have the other x squared. So this is really a negative times a positive times a positive times another positive, which is just a negative 1/2, or just negative. Okay, so I'm going to put that down here. So now I have enough information to graph this thing. So I'm going to plot all this stuff together and see how it connects. So x-intercepts at negative 2, 1, and 0. The degree is 5 and the leading coefficient is negative. So if the leading coefficient is negative, we've seen through our inductive reasoning that it ends going in the negative direction on the right-hand side. And since the degree is 5, the ends of the graph will go in opposite directions. So on the right-hand side, it's going to negative infinity. The one on the left is going to go to positive infinity. If the degree had happened to be even, one would have gone up and one would have gone down. Or sorry, they've both gone in the same direction. Okay? Now, going back here, the multiplicity comes into play here, where at x equals negative 2, the multiplicity was 2. Okay, so it's an even number of times it shows up. So at the x-intercept of negative 2, it will bounce off the x-axis. So it comes back up. The multiplicity at 0 is also even, so it'll come down, has to go pass through it, and it's going to bounce back. And then the multiplicity at 1 is just odd, or 1, which is an odd number, so it'll pass through. So it'll look something approximately like this. Now, for our purposes, we don't necessarily know how high either of these local maximums go. So we're just going to go ahead and draw them in just to show that we know the general shape of it. Okay? And that's as far as we need to go today. All right? right, hope this helps.